Welcome to the deep dive. Ever wonder what keeps the world turning? Quite literally.
Huh. It's often bearings, isn't it?
Exactly. Today, we're pulling back the curtain on something fundamental but maybe a bit overlooked. Bearings. We've waded through technical docs, catalogs from the big names like SKF, NTN.
The real experts in the field.
Yeah, to bring you the essentials. Our mission, let's say, is to give you a practical handle on bearing basics, from like figuring out which one you're holding,
Keeping them running smoothly.
right, without getting totally bogged down in the super technical jargon. Think of this as your express route to understanding something that seems complex. Honestly, I'm pretty excited to unpack this. It's amazing how much clever stuff is packed into these little things.
It really is remarkable. Bearings are, well, they're right at the heart of so much machinery. And just understanding them, how to care for them, it makes a huge difference in performance, longevity.
And avoiding headaches later on, I bet.
Definitely. What's really interesting is just how much information is encoded in those numbers stamped on the side and the precision needed to handle and install them properly.
Okay, yeah, let's get into that coding.
Wow.
Because you look at a bearing number and sometimes it's just noise. But there's a logic, right? Like SKF's system for standard metric ball and roller types?
There is, yeah. A pretty neat system, actually.
So if you see like a two-digit code, 0000010203.
Those usually tell you the bore diameter directly. So 00 is 10 millimeters, so O1 is 12, O2 is 15, and O3 is 17 millimeters.
Ah, okay, so just glancing at those first couple of digits gives you a key dimension, saves time, maybe stops you ordering the wrong thing. Pretty smart.
It is. And, like any good system, it has ways to handle the exceptions.
Really small ones or massive ones?
Exactly. Bores under 10 millimeters or over, say, 500 millimeters. Instead of that code, the size is usually just given straight in millimeters, separated by a slash.
Oh, like 6188, that kind of thing.
Precisely. That 8 just tells you it's an 8 millimeter bore. Simple. And the same thing applies to some standard ISO bearings too, ones with 22, 28, or 32 millimeter bores. You might see, say, 62 on 22.
So the slash is like a little flag saying, hey,
Yeah.
this number is the size. Got it. Now, what about the letters? You often see letters mixed in there. They're not just random.
Oh, definitely not. They tell you the type of bearing. So a seventh often means a single row angular contact ball bearing. And N points to a cylindrical roller bearing.
Okay.
And with cylindrical rulers, it gets even more specific. You might see combinations like NJ or NU. Those tell you about the number of roller rows or maybe the flange design, how the rollers are guided.
Huh.
Then you've got T, generally for tapered roller bearings that meet ISO standards, or C, 4C ARB toroidal roller bearings. Those are pretty neat, designed to handle shaft misalignment.
It's like learning a whole new alphabet. And I guess different companies might add their own twists. Looking at some NTN stuff for tapered rollers, they'd use prefixes and suffixes.
They do.
Like SL, meaning it's got some special polymer lube inside already. Or SW for a slot or keyway.
That's right. Those little additions can tell you very specific features. And as NTN points out, some of those mean the bearing isn't interchangeable with one that looks similar but lacks that code.
So you really have to pay attention to the whole number when replacing one. Can't just get close enough.
Absolutely critical. You need the exact match.
Okay, so hopefully that clears up some of the identification mystery. Now let's talk about what happens before they even get near a machine. Storage and handling. Sounds like they need a bit more TLC than, say, a bag of bolts.
That's a very good way to put it, yeah. Both SKF and NTN really stress proper storage. You're looking at a cool place, definitely dust-free, decent ventilation, but crucially controlled humidity.
Humidity control. Why is that so key?
Rust, basically.
Yeah.
Even tiny amounts of moisture over time can cause corrosion on those super precise surfaces. And that applies to the bearing units and housings too, not just the bare bearing.
Right, so even if they look tough, they can degrade just sitting on the shelf if it's damp.
Exactly. It could lead to failure right after installation, even if it looks fine.
And SKF mentions shelf life, right? Even for their open bearings. Something like 5 years.
Around 5 years, yes. That's thanks to the rust-inhibiting coating they put on and the packaging they use, which is longer than you might guess, actually.
It is, but what happens after 5 years? Just toss them.
No, not necessarily. SKF advises following specific guidelines then, basically inspecting them to make sure they're still okay. And of course, handling them carefully all the time is vital. No dropping them.
Yeah, you don't want to dent those perfectly ground surfaces. Makes total sense. Okay, let's move on to actually installing them. Mounting. Feels like there's a real science to this, more than just, sliding it on.
Oh, that's putting it mildly.
Yeah.
A really critical step before you even think about putting it on the shaft is measuring the radial internal clearance. SKF highlights this.
Internal clearance. So the amount of wiggle room inside.
Sort of, yeah. Think of it like the tiny bit of play inside the bearing. It needs to be just right, not too tight, not too loose, for it to work best. You need to know what it is before you start and how much it's going to shrink when you mount it.
Shrink. Why does it shrink?
Because mounting usually involves an interference fit. The inner ring is slightly smaller than the shaft, or the outer ring slightly smaller than the housing bore. When you press it on, the rings stretch or compress slightly, and that reduces the internal space.
Okay. So you measure it first, then figure out how much tighter it'll get. Getting that clearance reduction right is important.
Very important. It affects load distribution. Now, for the mounting itself, for bearings with a straight cylindrical bore, we usually talk about cold mounting.
Cold mounting, meaning no heat involved.
Right. Using mechanical force, but in a controlled way. With the right tools, applying pressure only to the ring being fitted.
Not just hammering it on then. I've maybe seen that somewhere. Definitely not hammering directly on the bearing. Use sleeves or press tools. Now, for bearings with a tapered bore where the hole gets slightly narrower, you might use special lock nuts or even hydraulic nuts for larger ones to push the bearing up onto a tapered shaft or sleeve until you get that perfect tight fit.
Hydraulic nuts. That sounds serious.
It allows for very precise control of the mounting force, and SKF recommends using a special paste molybdenum disulfide on the threads and nut faces. It reduces friction, helps you get really even tightening.
Like an anti-seize?
Sort of, but specifically for achieving the right mounting force. And a general rule for any cold mounting, always a thin coat of light oil on the mating surfaces first helps things slide together smoothly.
Good tip. Lube is always your friend. Now, you mentioned sleeves. Sleeve mounting. Adapter sleeves, withdrawal sleeves. What's the idea there?
Exactly. Using an adapter sleeve is common. You usually take off the nut and the locking washer first, coat the sleeve threads with oil, slide the sleeve onto the shaft, then position the bearing onto the sleeve's tapered surface. Then you tighten the nut to drive the bearing up the taper.
And that gives a secure fit without pressing directly on the bearing itself.
Right. It's often easier, especially on shafts that aren't perfectly uniform.
Yeah.
And there are very specific tolerances for these sleeves, too, to ensure the whole assembly works correctly.
Okay, cold mounting for smaller ones, but the really big bearings, that's where heat comes in. Induction heaters.
Precisely. Induction heaters are great. They heat the inner ring quickly and evenly, making it expand just enough to slide onto the shaft easily. No force required.
Nice.
And SKF makes a good point about their heaters having an automatic demagnetization cycle. That's really important
Demagnetization? Why?
because the heating process can magnetize the bearing. If it stays magnetized, it can attract tiny metal particles later on, contamination, which is, as we'll see, really bad news. So demagnetize before it leaves the heater.
Another one of those details you wouldn't think of. They also mentioned aluminum heating rings.
Yes, another method. With those, you need to coat the inner ring raceway with a specific oil first one that won't break down at high temperatures, protects the surface during heating. Then after it's mounted and cooled, you have to clean that oil off thoroughly.
Seems like every method has its own little checklist. Now, what about sealed bearings? You can't exactly measure the internal clearance easily on those. They mentioned a drive-up method.
Oh yes, the SKF drive-up method. It's
Yeah.
particularly for sealed spherical roller bearings with a tapered bore, and also for CARB toroidal bearings. It's a very precise technique. Instead of measuring clearance directly, you measure how far you push the bearing axially up the taper,
By angle or distance.
usually by measuring the axial distance very carefully. This calculated drive-up achieves the correct reduction in internal clearance. It's vital for allowing the shaft to expand thermally during operation.
Especially with those CARB bearings, right? Because they're designed to handle shaft movement.
Absolutely crucial with CRB bearings. They need space on either side to accommodate that axial movement. The drive-up method ensures they're mounted correctly to allow for that.
So it's not just getting it on, it's thinking about how the whole system works together. What about mounting whole bearing units and housings? That looks simpler.
It might seem simpler, but still needs care. You typically put the bearing in the housing base, put the cap on, align the whole thing using the shaft itself, then tighten the housing bolts. And crucially, tighten them to the recommended torque, usually in a sequence.
And these units can handle a bit of misalignment, usually.
Often, yes. Maybe up to 2 degrees if you relubricate them, sometimes even 5 degrees. But big caution here, pressed steel housings don't really tolerate much misalignment once they're bolted down tight.
Yeah,
They can distort the bearing.
Good point. And mounting units onto adapter sleeves. Similar idea to the bare bearings.
Pretty similar. Position the unit on the sleeve, put on the lock washer, then tighten the lock nut. But here, you often tighten it to a specific angle of rotation, like around 70 degrees past hand tight is a common figure, or to a torque spec. And you need to make sure the sleeve doesn't spin while you're tightening, and that the shaft can still move actually as intended.
Okay. And for the non-locating units, the ones that use those locking collars with the little screws.
The ones with grub screws, yeah. There, you position the shaft actually where you want it, then tighten those grub screws in the collar, again, to very specific torque values. For these floating bearings, you usually try to install them roughly in the middle of their allowed axial travel range.
To give room for thermal expansion either way, makes sense. They also mentioned, really briefly, using hydraulic pressure for mounting really huge tapered bore bearings.
Yes, for the really big ones, the forces needed for a proper interference fit are just enormous. So they use hydraulics to push the bearing on, often combined with oil injection. Yeah, pumping a thin film of high-pressure oil between the bearing bore and the shaft seat. It basically floats the bearing slightly, drastically reducing friction, makes mounting much easier, and needs less force from the nut. Pretty clever stuff.
Wow, okay. So we've got them identified, stored carefully, mounted securely. Now, keeping the bad stuff out, seals. Lots of different types mentioned. Labyrinth, V-ring, felt, taconite. That's a whole other component category.
It really is. And each type, often with its own code like TSD, TSN, B, EPR, LER, is designed for different jobs. A labyrinth seal is non-contacting, good for higher speeds maybe, while a taconite is like a multi-stage fortress for really harsh, dusty places.
And getting these seals installed right is just as important as mounting the bearing, yeah. Otherwise, they don't do much good.
Absolutely critical. Cleanliness, again, is key, using the right tools, and the surface on the shaft where the seal lip actually runs the counterface, that has to be perfect. Smooth, round, clean.
What if it's not perfect? Worn shaft.
Well, ideally, you'd repair the shaft. But SKF makes a handy thing called a speedy sleeve. It's a very thin sleeve you put over the worn area to give the seal a fresh surface.
Neat repair trick. And prepping the shaft edge before sliding the seal on?
Essential. You need a chamfer or a radius, a slight rounding on the shaft end. A sharp edge can easily cut or damage the seal lift as it goes on.
Ouch.
And usually, unless it's a special dry-running PTFE seal, you lightly coat the seal lip with whatever lubricant you're using in the bearing. Helps it slide on and bed in. When pressing it into the housing, use a mandrel, a tool that presses evenly on the seal's outer metal casing. Don't just push on the soft part.
Right. Keeps it going in straight and true. Okay, seals in place. Let's talk alignment, getting things lined up properly. They mentioned soft foot. What on earth is that?
Yeah, soft foot. It's when a machine's mounting feet don't sit perfectly flat on the base plate. One or more feet might have a gap underneath.
Like a wobbly table.
Exactly like a wobbly table. It puts stress on the machine frame, can distort things, cause vibration. There's parallel soft foot, just a gap. An angular soft foot, where the foot's kind of twisted.
And the fix is usually shims, those thin metal plates.
Shims are the classic fix for parallel soft foot. You measure the gap, put in the right thickness of shims. Angular's trickier, might need machining or special adjustable feet. SKF makes things called Vibracon SM, which are adjustable chocks, a more engineered solution.
So getting the machine sitting solid is step one. Then you align the shafts connecting to it, right? They mentioned rough alignment first.
Yeah, rough alignment is just getting things close enough to use precision tools, maybe within, say, a millimeter offset and angularity around 0.1 millimeters per 100 millimeter. Just eyeballs or a straight edge and feelers might get you there for the rough part.
Gets you in the ballpark. Okay, machine's flat, shafts are roughly lined up. Now, the lifeblood, lubrication. Let's start with grease. It's not just generic gunk, is it?
Oh, definitely not. Grease is basically oil, held in a thickener. Think of the thickener like a sponge. It holds the base oil, which does the actual lubricating, and releases it slowly.
What kind of thickeners?
Most common is a soap-based one, usually lithium soap. Very versatile. But you also get calcium, sodium, aluminum soaps, and non-soap thickeners too. For higher temperatures, you often see complex soap greases.
And the oil itself, mineral oil.
Mostly mineral oil, yeah. But you also get synthetic base oils for extreme temperatures or specific needs, even some natural ones. Plus, grease has additives, anti-wear, rust inhibitors, that kind of thing.
So lots of ingredients. And
Yeah.
temperature seems critical for grease. They talked about LTL, HTL, SKF's green zone.
What's that about?
Right. LTL is the low temperature limit, the coldest it can get before the grease is too stiff for the bearing to even start easily. HTL is the high temperature limit, basically close to the dropping point where the thickener lets go of the oil.
So you want to operate between those.
Ideally, well within those limits. SKF's green zone on their charts shows the recommended performance range, where the grease works reliably and predictably for its expected life. Stay in the green.
Got it. Keep it in the happy zone. What about speed and load? Do they affect grease choice?
Hugely. Speed is often looked at using a K-factor relates bearing size and RPM. Greases are rated for certain speed factors. Load is usually considered with the CP ratio, the bearing's load rating versus the actual load. Higher CP means lighter load.
And those NLGI grades, numbers like 0, 1, 2 on the tube.
That's the consistency, how stiff the grease is. NLGI2 is probably the most common multi-purpose grade. Softer grades like 0 or 1 might be used in gearboxes or central systems. Stiffer ones maybe for vertical shafts to prevent slumping. NTN mentions this link to application.
Makes sense. And other key properties, like how well it resists water.
Yeah, water resistance is important, often rated by tests like the EMCR test, which also checks corrosion protection. You also care about oil separation. You want the oil to bleed out slowly, not all at once or not at all, and just general corrosion protection.
Now, one thing I've heard warnings about is too much grease. They cautioned against overfilling. Why is that bad?
It really is bad. If you pack a housing full, the bearing has to churn through all that grease. That generates a lot of heat, can raise the temperature 50 degrees C easily.
Wow, so it cooks the grease.
It can degrade it quickly, burn it even, and ironically, churning can push grease away from where it's needed. So unless you're doing a special run-in procedure, SKF says fill maybe only 30% of the free space in the housing. Less is often more.
Good rule of thumb. Don't just pump till it oozes out everywhere. They also mention a specific technique for greasing CARB bearings with cages at high speed.
Ah, yes. For those, you want to make sure you apply grease specifically to the guiding surfaces of the rollers and the cage itself. Ensures those critical contact points get lubed properly, especially when things are spinning fast.
Okay, that's grease covered. What about oil lubrication? When would you choose oil instead?
NTN points out oil is generally better for really high speeds or very high temperatures, or when you need to actively remove heat from the bearing. Oil can circulate and be cooled.
And the key with oil is viscosity, right? Getting the right thickness for the temperature.
Exactly. Viscosity is paramount. You need the right viscosity at the operating temperature. Standard mineral oils often work fine, but synthetics might be needed for extreme hot or cold.
And choosing the right oil involves looking at, well, everything.
Pretty much. The application, bearing type and size, the load, temperature range, speed, shaft orientation. Is it horizontal or vertical? Any external factors like vibration, contamination risk, all play a part. There are standard ISO viscosity grades, ISO VG numbers, to help classify the thickness.
So a careful analysis needed. Now, a big enemy for both grease and oil, contamination. What does dirt actually do inside a bearing?
Even tiny solid particles are killers. They get rolled over by the balls or rollers, creating tiny dents, indentations in the super smooth raceways. These dents often have raised edges.
Like little bumps.
Exactly. And those bumps act as stress risers. Over time, fatigue starts there, leading to flaking or spalling little bits of metal breaking off. Plus, contaminants cause abrasive wear. So keeping lubricant clean, handling bearings carefully, it's non-negotiable.
Even lint from a rag could be bad.
Potentially, yes. Anything that isn't clean lubricant.
Sobering. On a related note, they mention centralized lubrication systems. Sounds efficient.
They can be very efficient. A central pump and reservoir feeding lubricant oil or grease up to NLGI2, usually through lines, to all the different lubrication points. Delivers the right amount at the right time automatically.
Less chance of someone forgetting to grease a point.
Exactly. Reduces human error, ensures consistency. Maintenance is mostly just refilling the reservoir and checking for leaks. Great for big machines or hard-to-reach spots.
Smart automation. Okay, but things still go wrong sometimes. Bearings fail. They listed common causes of damage.
Yeah, the main ones are often material fatigue, just wearing out from normal stress cycles, causing that subsurface spalling. Then there's inadequate lubrication, metal-on-metal contact, causing wear, heat, seizure. Contamination, we just talked about, dents, wear, corrosion from moisture or chemicals.
What about false Brinelling? Sounds odd.
That happens when a bearing is stationary, but subject to vibration. The rollers or balls hammer tiny indentations into the raceways. Looks a bit like Brinelling from impact, but it's from vibration. And then, improper fitting rings, creeping or spinning on the shaft or in the housing.
That's a good list. And they stress linking weird noises or vibrations back to these causes, right?
troubleshooting.
Yeah, that's key. That noise. Is it happening under load? Is it a rumble, a squeal? SKF has tables like diagnostic charts linking symptoms to potential causes, issues with axial drive up, outer ring rotation, rust, all sorts of things. Really useful.
Like a doctor diagnosing symptoms, they also mention specific issues with seals and housings.
Right. Seals installed wrong, worn out, leaking. They let dirt in, grease out. Housing problems too. Cracks, leaks, blocked vents preventing pressure release. And lubricant issues are huge. Wrong type, wrong amount, old or dirty lube.
And fits again. Too loose? Too tight?
Yep, incorrect fits cause all sorts of stress. Same with improperly clamped sleeves or lock nuts.
Yeah.
And one more electrical damage, if stray currents pass through the bearing, you can get etching or fluting on the raceways. Looks like tiny lightning strikes.
Wow, hadn't thought of electrical damage. So a lot can go wrong. Now, when you do need to take one out, dismounting, just as important to do it right as putting it in.
Absolutely. You don't want to damage the shaft or housing getting the old bearing off, especially if you plan to reuse those parts. Cleanliness is still important. Have the right tools ready. Solvents might be needed, petroleum cleaners, kerosene. SKF doesn't recommend chlorinated solvents, though, for safety and environmental reasons.
And they make special tools for pulling bearings off.
They do. Pullers are common. For small bearings, mechanical pullers that grip the inner ring are best, if you can access it. Self-centering pullers are good. Apply force evenly.
What if you can only grab the outer ring?
Sometimes you have to. Or use a puller with a back plate that sits behind the bearing. For bigger bearings, especially off tapered seats, you often need hydraulically assisted pullers again. Lots of force needed.
And heat can be used for dismounting, too.
Yes, sometimes carefully heating the inner ring can help loosen its grip on the shaft, making removal easier. There are specific techniques depending on whether it's on a cylindrical shaft, tapered shaft, in a solid housing, or on a sleeve.
So again, careful work, right tools. Lastly, they mentioned bearing arrangement, this idea of fixed and floating bearings. What's that about?
Fundamental concept. When you support a shaft, usually with two bearings, one needs to locate the shaft, actually stop it moving end to end. That's the fixed bearing.
Holds it in place.
Right. The other bearing, the floating one, is set up to allow some axial movement,
Why allow movement?
primarily for thermal expansion. Shafts get longer when they heat up in operation. If both bearings locked it axially, that expansion would create huge internal loads, stressing everything. The floating bearing accommodates that growth, and also minor mounting misalignments.
So the fixed bearing anchors it, the floating bearing lets it breathe, basically. Makes perfect sense. It's managing those expansion forces.
Exactly. Choosing the right fixed floating arrangement is a core part of machine design, as NTN also stresses, gets you reliability.
Well, this has definitely been a proper deep dive. We've gone from decoding the numbers to storing, mounting, sealing, lubricating, troubleshooting, dismounting, arranging. It's way more involved and fascinating than you might first think.
It really is. And look, while it sounds technical, getting a good handle on these basics really helps you make smarter decisions about machinery maintenance. It leads to better reliability, less downtime, saves money and frustration in the long run.
Absolutely. I really hope this session has given you, our listener, some genuinely useful insights, maybe sparked some curiosity about these often hidden mechanical heroes. So thinking about everything we've covered, what's one area of machine care you might look at with, well, completely fresh eyes now?
That's a great question to ponder.
Definitely check out the original SKF and NTN materials if you want to go even deeper. They're packed with detail. Or, reach out if you have more questions. Thanks for joining us on the deep dive.